So let's talk about the calculus of polar curves. So let's talk about like tangent lines and stuff. So we know for tangent lines, if you've got a point x naught, y naught that's on the graph, and you've got the slope of the tangent line, that's your dy dx at the point. Then the tangent line looks like y equals slope of the tangent line, x minus x naught plus y naught. So the question is, how does that translate into polar coordinates? You follow? If we're graphing a polar equation in the xy plane, I've got to somehow get back to x's and y's. And as you saw in the homework from last week and some of the examples we did, trying to convert a polar equation back to rectangular coordinates can be a little bit of a nightmare. Okay? So here's the good news, is we've already done the work that we need to have this happen. Because if we think of r as a function of theta, and we think of x as r cosine theta, well, that's like having x be a function of theta, cosine of theta, y is r sine theta, that's f of theta, sine of theta. We can think of the polar curve as being a parametric. So r equals f of theta, we can think of this as a parametric situation with x and y being functions of theta. You follow or not? And so we know how to get dy dx with parametrics, courtesy of the chain rule. So we know how to get dy dx in terms of thetas, courtesy of the chain rule. So in other words, dy dx would be dy d theta divided by dx d theta. And so let's look at what that would be. Dy d theta, y is f of theta sine of theta. So we take the derivative of that with respect to theta. Gonna have to use a little product rule there. So it would be f prime of theta sine of theta plus f of theta times the derivative of sine of theta cosine theta. And then what would dx d theta be? Would be f prime of theta cosine of theta minus f of theta sine of theta. And so there it is. So there's the dy dx slope. There's the slope of the tangent line as a function of theta now. So one thing to note, when we were graphing these things on Thursday, let's say you're graphing this in the r theta plane, r equal f of theta, and let's say that, whoops, I'm going to do that. And let's say we had a point here, we'll call it alpha. So that the r equals f of alpha is 0, but the derivative is not 0. All right? We use such points, we called them the tangent at the pole. We said, okay, well, this is the angle through which the curve is going to pass through the origin. You follow? And I said we would actually prove that fact on Monday, so here we are. So notice if this is the case, what would the slope be, dy dx? At such a place will it be f prime of alpha sine of alpha plus f of alpha cosine alpha divided by f prime of alpha cosine alpha minus f of alpha sine of alpha. And if I use my information I've got here, the r value is 0. That means we're at the pole. So these terms will cancel out. And I'm left with f prime of alpha sine theta over f prime of alpha cosine theta. The fact that f prime of alpha isn't 0 means I can cancel these out. And I get sine theta over cosine, I get f prime of alpha sine alpha over f prime of alpha cosine alpha. Since f prime of alpha is not 0, I can cancel them out. Sine over cosine is tangent. And so this tells me the slope of the tangent line at the origin is tangent alpha. And so this means on the xy plane, if I look at the line y equal tangent alpha x, this is the synonymous with the line theta equals alpha. This then is going to be the tangent to that curve at the pole. So that's the calculus proof of what we had talked about. Makes sense or not? So it works. Okay. So really, when they ask about tangent lines with polars, you just do the same thing you did as when you had parametrics, except that's the formula you use to get dy dx. You just plug in your theta values. So as an example, locate the points where the curve r equal 1 minus 2 sine theta has a horizontal tangent line. So locate the points. So we'll take a look at this curve here. R equal 1 minus 2 sine of theta. I know that, once again, dy dx is dy d theta over dx d theta. And I know from parametrics, horizontal tangents are going to happen when the numerator is 0, but the denominator is not 0. Okay, so that's what we had when we did parametrics. So let's take a look at what we got here. So y is r sine of theta, which in this case r is 1 minus 2 sine of theta. Sine of theta, which is going to be sine of theta minus 2 sine squared theta. And so we'll look at dy d theta and see when that's equal to 0. So I need the derivative of sine of theta, which is cosine of theta, minus, what's the derivative of 2 sine of theta squared? So the 2 comes down, multiplies the 2 that's there, and gives us a what? 4 times the sine of theta times the derivative of sine, which is cosine. Everybody good getting us to this point? All right, now I got to look where this is equal to 0. Notice, what can I do with the cosines? Factor them out. 1 minus 4 sine of theta is 0. And so we get either the cosine of theta is 0 or 1 minus 4 times the sine of theta is 0. And so I'll copy this down here, and then we'll do the unit circle work here. Sine of theta would be a quarter then. So here we go. Looking at the old unit circle here. Cosine of theta is 0 when theta is what? Here and here. And so what are those angles? Pi over 2, 3 pi over 2. Good. Now let's look at where the sine of theta is a quarter. So if sine is positive, that puts us in what two quadrants? 1 and 2. A quarter, that's not one of the usual values, right? A half is, but not a quarter. So we'll call this angle here alpha. So we need an angle whose sine, we need an angle in quadrant 1 whose sine is a quarter. So that's going to be the inverse sine of a quarter. And then to get this angle here, I have to back up a quarter. So pi minus that. So those would be the 4 places. Whoops, these are thetas then. So theta would be this, and theta would be that. So these are the 4 places where dy d theta is 0. But I have to check to see if any of these are duplicated with where dx d theta is 0, right? Because if the x d theta is also 0, the parameterization is not smooth. We have to see what's going on there. So let's look at x, remember, is the r cosine of theta. So in this particular case, it'd be 1 minus 2 sine of theta, cosine of theta. So it would be cosine of theta minus 2 sine of theta, cosine of theta. And now we need to get dx d theta. Derivative of cosine minus sine. And then what rule am I going to have to use here? So product rule, derivative of the first times the second plus the first times derivative of the second. So I get a minus sine of theta minus 2 cosine squared of theta minus minus plus 2 sine squared of theta. And if I'm going to set this equal to 0, I got to get everything in terms of either sines or cosines. You follow? So what can I do? How can I exchange cosine squareds to sine squareds? Cosine squared is what? It's your 1 minus sine squared. So now I've got minus sine theta minus 2 plus 2 sine squared theta plus 2 sine squared theta is 0. And now if I gather everything together, I have how many sine squareds total now? 4 of them. Minus a sine theta minus a 2. So we got a quadratic in terms of sine. Is it going to factor nicely for us? Well, we could check. We could check the old discriminant here. What's the discriminant work out to be? I got a 1 plus a 32, right? Which is a what? 33. So that tells us it's not going to factor nice, but it does tell us we'll get two answers. We'll get that the sine of theta is either 1, it's 1 plus or minus the square root of 33 all over 8. Now the question is, do any of those angles match the angles we got from dy d theta? Because from dy d theta equals 0, we got pi over 2, we got 3 pi over 2, we got the inverse sine of a quarter, and pi minus that. The sine of these two angles are either plus or minus 1. You follow? Am I going to get plus or minus 1 for the sine of him? The sine of these two angles are a quarter. Are you going to get a quarter out of this? So the sine of these angles is not plus or minus 1. And the sine of the angle here is not going to be a quarter. So I have no duplicate solutions. Make sense or not, folks? So this says that all the things we got from dy d theta, those are all going to be places where we have the horizontal tangents. Okay? I don't have to throw any of them out. So now we just have to go through and find the points that are on the graph. So we have we have x is our cosine theta, which is 1 minus 2 sine of theta, cosine of theta. And we have y is our sine of theta, which is 1 minus 2 sine of theta times sine of theta. And let's plug in our thetas. So let's do theta equals pi over 2. Let's figure out what the x, y coordinates are. You plug in the pi over 2 into here. You get the cosine of pi over 2, which is what? 0. 0 times anything is 0. Now you put the pi over 2 into here. The sine of pi over 2 is 1. 1 minus 2 is negative 1. So 0, negative 1. This is an xy point. So when we graph it on the xy plane, this is one point where we expect to have a horizontal tangent line. Let's put in theta equals 3 pi over 2. Once again, the cosine of theta is 0. That's going to 0 the x out. You plug the 3 pi over 2 in. The sine of 3 pi over 2 is a negative 1. So we're going to have a 1 plus a 2 times a negative 1. So the xy value is 0, negative 3. Now let's look at these other two. We got theta is the inverse sine of a quarter. Well, the good news is we know that the sine is a quarter. The bad news is we don't know off the top of our head what the cosine is, but we can find it. Because sine is the ratio of what two sides? Opposite over hypotenuse. So Pythagorean theorem says that missing side is what? The square root of 15. So that's square root of 15 fourths. So let's see, x would be 1 minus 2 times the sine of theta times the cosine of theta. So I get 1 minus a half, which is half, times root 15 over 4. So root 15 over 8. I'm going to put this right over here. Y is 1 minus 2 sine times sine, which would give us 1/8. You follow or not, folks? Okay. And then for our last point, theta is pi minus the inverse sine of a quarter. And once again, unit circle, we're over here now. So the sine of theta is still a quarter, but the cosine of theta would be what? Well, we know that in quadrant 1, the cosine is the positive root 15 over 8. Or excuse me, root 15 over 4. So in this quadrant, it would be negative root 15 over 4. You with me or not? So the only thing that would be different in my calculation is right here. So instead of x being a positive root 15 over 8, x would be what? A negative root 15 over 8. The y value would be the same because the sine is the same. And r and y only depend on the sine. Of course, what's the ultimate check here? Fire up Desmos, regraph this curve, put in those points, and we should see that the curve should be locally flat. So let's do that. So once again, if you type in r's and thetas, it automatically will convert it to polar for you. There we go. We put in our points here. We've got what were all the points we got? We got 0, -1, 0, -3. And we had square root of 15 over 8, comma 1 over 8. And then we had the symmetric point here. I can zoom in there. And let's type in the y values for all of these things. And you can zoom in. Is it working or not, folks? Locally flat there. Locally flat there. then we've got up here. It's the same tangent line for both of them. Make sense or not, folks? Okay, so that's how you do it. So if you're doing tangent line stuff with polars is the same as tangent line stuff with parametrics. Your R is your f of theta. All right, now let's talk about area. So let's start back with, in Calc 1, you had a continuous function over an interval AB, and we were looking where f of x was greater than or equal to 0. So it looks like this. Oops. We were interested in figuring out what the area was between the x-axis and the curve. So A is the area between y equals 0 and y equals f of x. You follow? And how did we set about this problem? The one thing we knew how to find areas of were rectangles. So we went in there and we chopped up the domain. We chopped up the inputs. So chop up inputs until we got little things, little widths of delta x. And then we sampled the function at some point, whether it was the left endpoint, the right endpoint, or the midpoint. We sampled the function somewhere in that little interval, and we had a rectangle of area, height times width, f of xi star times delta xi. Does this story sound familiar? Right. And so the area that I wanted was approximately equal to the sum of the areas of these rectangles. Well, once again, we had the height of the rectangle times the width of the rectangle. And how did we get the actual retail value of this? We took a limit as n went to where? Infinity. That's assuming the delta x's went to 0. So assuming that the delta x's went to 0 that way. And then what popped out, of course, was our friend the definite integral, where the integral sign was the continuous version of the summation. The f of x sub I star became the integrand f of x. The delta x sub I, the change in x, became the infinitesimal increment dx. Okay, remember that story? Now you're going to see this story over and over again between now and the end of the semester, because we're going to be going in over and over again, and we're going to be chopping stuff up, sampling something, adding it up, and then taking a limit, and an integral will pop out. So it's, once again, very nice that this shows up here, because we have to now think polar coordinates. So what's the analog in polar coordinates? All right, in polar coordinates, it's not y's and x's, but r's and thetas. You with me or not? So r's and thetas. So we're going to have r equals f of theta. We're going to need it to be continuous, and we're going to need it to be bigger than or equal to 0, although it ends up, it'll be fine anyway. And we're going to look at the area between r equals 0 and r equals f of theta. You follow? You see how that'd be the natural analog here? So what's that look like, though, in polar coordinates? So once again, we're graphing these polar curves on the xy plane. So we're going to have r equal f of theta. We're going to have f be continuous over an interval of thetas. So we'll call it alpha and beta instead of a to b, because those are Greek letters. Those are the angles. And r equals 0, Well, remember, when r equals 0, that sits you right down at the origin. You follow? So here's the r equals 0. And then here's the, say, theta equals alpha. And here's theta equals beta. And then you've got some r equals f of theta. So the area we'd be looking at would be that area there. Does that make sense or not? Do you see how that's the analogous problem? So how do we handle this? The same way we handle this. We're going to chop up the inputs. You follow? But the inputs here aren't x's. The inputs are what? Thetas. So we're going to chop up thetas. Have our little delta theta I. Now what's that look like geometrically? If you're chopping up thetas, thetas rotate counterclockwise, you follow? We're rotating from alpha to beta. So when we chop up the thetas, you follow? That's what it's going to look like. These are your delta thetas. You with me or not? Okay. And now we're going to sample the function r equals f of theta I somewhere in between and use that to make a constant. So over here, what did we do? Right? We looked at y equals f of x to be approximately f of x star. And so that flattened it out at the top. You follow? That made it a constant. Now over here in r theta land, we're going to have a constant radius. Constant radius in polar sweeps out a circular arc. You with me or not? Okay. So, like over here, I would pick some r value, say like right there, and then I'd be looking at approximating this by a sort of a pi wedge. So if I kind of blow this up a little bit, I got my angle in here is delta theta sub I. And let's say, you know, this is r at theta sub I star. And then, you know, it's just I'm approximating what the polar curve is doing through that entire interval by looking at what's happening there. You with me or not, folks? So I need the area of this wedge, which, well, you can, like a slice of pizza or something, which more technically is called a central sector of a circle. All right, so I need to figure out what that is. So we go off to a little geometry. Let's say we have a circle. Let's say we have big radius big R. Let's say we have some angle, once again measured in radians, and we'll call that angle gamma, because we've already got alpha and beta in play elsewhere. The area of the sector is to the area of the circle. All right, so that's my unknown. Should be the same ratio as the angle measure of gamma to the angle measure of the whole circle. So how many radians are in the entire circle? 2 pi. Does that make sense or not? This is the proportionality of the circle. The circle is perfectly round. It's perfectly proportional. So this you see this all the time in these arguments. So the area of the sector is gamma over 2 pi times the area of the circle. And what's the area of the circle? Well, that's pi times the radius squared. And so you get one of the r's cancel, or the pi's cancel. I get 1/2 r squared gamma from that. You follow? You may know this from geometry, I don't know. 1/2 r squared gamma. So that means that my area here is 1/2 r of theta sub I star squared times delta theta sub I. Make sense or not, folks? Now this would be the area of just one of those wedges. To get the area of the region, I take the area of each of those wedges and add them up. And that would approximate the area of the entire region I want. So the area I actually want would be an approximate sum. I goes from 1 to n, 1/2 r of theta sub I squared delta theta sub I and then you do the thing. The 1/2 is a constant. You're going to the discrete sum turns into the continuous sum. What are we summing up? Our integrand would be r of theta squared d theta, and that's your area formula in polar coordinates. This is the area between the pole and the curve. As I tell students, day 1 of Calc 1, calculus equals pre-calculus plus limits. Here it is again. We've got the pre-calculus notion, area of the sector of a circle. We're slicing the area of the, we're slicing the region we want up into very, very small little pieces. Each piece, we're finding the area of, adding those things together, and then taking a limit. So we're taking a big thing, breaking it into small things, putting them back together, and taking a limit. Boom. That's integration in a nutshell. So here we go. That's the story of that equation. Common mistake, students forget two things. They forget the 1/2. They tend to forget the squaring as well. All right, so don't do that. All right, the strategy, sketch a detailed graph of the region and exploit symmetry wherever you can. So we're going to focus on setting these up. And then I'll leave the actual details of the integration to you. And I recommend you work through at least some of these. Let's take a look at number 1 here. Find the area of the following. The area enclosed by the inner loop of the graph of r equal 1 minus 2 sine theta. Well, as luck would have it, that's exactly the graph that we've been looking at. You follow? Do you see what they mean by the area of the inner loop? They mean this thing right there. You follow? So this is where graphing comes into play with how we graph stuff on Thursday. We've got a standard sine wave here. It's frequency 1. So it's going to go from 0 to 2 pi. The usual quarter marks. You plug the numbers in. You plug in 0, you get out 1. I'm sorry. These are pi over 2's. You plug in the pi over 2, now you're down at -1. At pi, you're back to 1. At 3 pi over 2, you're up to 3. 2 pi back to 1. Connect the dots in a pleasing fashion, and you know what is going to be important for us to find are those things there. Okay. Set these equal to 0. Sine theta is a half. What do you get for that? Where's sine theta a half? 1 theta is going to be what? Pi over 6, and then the other one's 5 pi over 6. And as we mentioned Thursday and we proved today, since these are values where the r is 0 but the r prime is not, these are the tangent lines at the pole. This tells you the angles through which we're dealing with. So when we go back and look at our Desmos graph, there it is. We know that the angle where it starts to dip through is pi over 6, and then it does its job and it comes back out at 5 pi over 6. You with me or not, folks? So that tells us that those are the limits of our integral. You see the connection or not? So that's what's really nice about this. So I know that my area is going to be, don't forget the half, 1/2 integral pi over 6 to 5 pi over 6, 1 minus 2 sine of theta, all squared d theta. Okay. But we can cut this down a little bit because of symmetry. We know that there's symmetry here. You follow? So instead of going from pi over 6 to 5 pi over 6, I could just go from pi over 6 to what? Pi over 2, and then do what with my answer? Double it. So I could do a 1/2, and I could just double 0 to pi over 6 to pi over 2. One minus 2 sine of theta squared d theta. In other words, it comes through here, pi over 6. I'll just find this area and then double it. So what happens to the half? It cancels out. Does that make sense or not, folks? Now, we're going to work through this integral. This will be the only one we work through because it showcases some of the techniques from the first week of school that I want to make sure that you remember in working through these problems. So let's just do the pi over 6 to pi over 2 one. The first thing you have to do with that integrand is what? FOIL it out. So when in doubt, write it out. You got 1 minus 2 minus 2 minus 4 sine of theta plus 4 sine squared of theta d theta. And the 1 we can integrate right away. 1 d theta is going to give me what? Theta. Minus 4 sine theta integrates to what? 4 cosine theta. And this is from theta equal pi over 6 to theta equal pi over 2 plus 4 times the integral from pi over 6 to pi over 2 sine squared theta d theta. And this is where I just want to remind you of this, because if you look, you're always squaring the r. You follow? So you're always going to get like sine squareds and cosine squareds popping up. And so how do we handle that? This is what I wanted to remind you of here. Sine squared of an angle, how do I reduce the power? What's the reduction formula? It's 1 minus cosine of twice the angle over 2. This makes the calculus easier. It makes the algebra harder, but the calculus easier. And likewise, cosine squared of theta is 1 what? Plus cosine 2 theta over 2. So these things are going to come in handy, folks. So just remember those. So we'll go to the next page here. This will be whatever it is. I don't really care about this. The arithmetic at this point. This will pop out a 4. One minus cosine 2 theta over 2. And then you're on your way. So you're going to get a theta plus a 4 cosine theta. You've got the 4 over 2, which is a 2. That gives you a 2 theta. You're going to get a minus 2 cosine 2 theta. That's going to integrate to a minus sine of 2 theta. And once you go through that arithmetic there, you're going to get your answer, which will be square units because it's an area. Make sense or not? So once again, this is good review. It harkens back. This kind of integration of these trig functions, this is all section 8.3. So those, you're going to get your trig integrals with sines and cosines. So, you know, dig up the handouts. Got all the identities on there for you. Okay, let's look at number 2, the area between the loops. So once again, you got to do a little bit of work to see what the heck they even mean by the area between the loops. So I go back to our graph. There it is. What do you think they mean by the area between the loops? You follow or not? That makes sense? Now here's the thing with the area between the loops. When you do this area formula, this is specifically between the pole out to the f of theta. You with me? We're always going from the pole out. So here's what we got to do. This here is the inner loop. You follow? So the outer loop is going to go from 0 to pi over 6, and then 5 pi over 6 to 2 pi. You with me or not? Now we can check that on Desmos. Zero to pi over 6 is what I love about this. And then 5 pi over 6 to 2 pi. Right? You with me or not? So if I do, I'll call it A1 is 1/2 integral 0 to pi over 6 of 1 minus 2 sine of theta squared d theta. That's going to give me that piece of area. You with me or not? And if I do A2, 1/2 integral 5 pi over 6 to 2 pi 1 minus 2 sine of theta squared d theta. That's going to give me, once again, from the pole out, all of that area. You follow or not? Okay. So to get the area between the loops, I would have to add these two together. And then subtract off what? The area I found of the inner loop. Does that make sense or not, folks? Okay. You see how you have to piece these together? And you got Desmos here. If you're unsure, that's what I love about Desmos. Graph it and then change the theta to your limits. And just, once again, you're going from the pole out. So you're going from the pole out to each of these things. And the area that you cover from going to the pole out for those angles is exactly the area that you're calculating with that integral. You follow? So you'll see that here in the answer. So you got this. This was like the A1 we had. This was the A2 we had. And I'm subtracting off number 1 there, because that was the area we got for number 1, which was the inner loop. So you really need to have your trigonometry to help you get that first graph, and then the geometry to help you connect everything up. You follow? Now, let's see how we can use symmetry. So here's using symmetry, I'm just doing this. So I'm replacing A1 and A2 with this integral here. Well, the integral goes from where to where, folks? 5 pi over 6 to 3 pi over 2. So what's happening? If I look at my graph, (5 pi over 6 to 3 pi over 2). Look at what's going on there. You follow? That's sweeping out exactly half of the outer loop. And so if I go in there and find the area, once again, sweeping from the pole out to the curve, I could just double this area. And then subtract off the inner loop. You with me or not? So once again, you want to exploit symmetry as you can, because that'll cut down on the number of integrals you have to evaluate. And oftentimes plugging in like a pi over 2 or a pi or a 2 pi is a much easier calculation when you got sines and cosines involved, right? Because that's half the time that'll cancel out. All right, let's take a look at the area enclosed by one leaf of r equals 4 cosine 2 theta. So first off, let's graph it. What do they mean by one leaf? Let's go 0 to 2 pi and see if that gives us what we need. There it is. Ah, there you go. Do you see what they mean by one leaf? Right? So we got to figure out what's going to generate that. So we go back to trigonometry. We look at the graph on the r theta axis here. 4 cosine of 2 theta. This cosine function has a frequency of 2. That means it's going to go twice as fast. So instead of going between 0 and 2 pi to complete a cycle, it's only going to need 0 to what? Pi. Put that in there. We'll chop that up into 4 equal pieces. And now we'll plug in the quarter marks and we'll see where we're at. You plug in the 0, cosine of 0 is 1 times 4. You're up at 4. So we're starting up here at 4. Pi over 4, you double that. That'll get you to pi over 2. That's where we zero out. Pi over 2, you get the cosine of pi, which is negative 1. Now we're down at negative 4. 3 pi's over 4, double that, 3 pi over 2. Back up here. So once again, we see we're crossing through the theta axis at pi over 4 and 3 pi over 4. That produces the tangents at the poles. So here's the pi over 4. Here's the 3 pi over 4. So if we want the area of one leaf, what do you notice? I sweep out half the leaf between theta is 0 and theta is pi over 4. You follow? So all I would have to do is take that area and do what with it? Double it. So the area would be double what I would get going from 0 to pi over 4. 4 cosine of 2 theta squared d theta. Does that make sense or not, folks? Do you see how we're getting the right integral to correspond to the right region? That's the key. Just graph it. You graph it. You graph it the way we did on Thursday. That's going to help you find the limits on your integral, and then use the symmetry. And once again, once you would square that out, you'd have to use your reduction formula to actually evaluate that integral. Let's look at the last one. We want the, oops, there's a typo. You see the typo here? That should be 2 thetas in there. Last one, we're looking at r equal 4 cosine 2 theta, and then r equals 2. So once again, we want to graph it. There's r equal 4 cosine 2 theta. What does r equal 2 look like? The radius is always what? 2. The angle can be whatever. There it is. Do you see what they mean by common interior? They want the area that's inside both. You with me or not, folks? Now, what do you notice? There's 4 symmetric parts to this area, and each of the symmetric parts is made up of 2 symmetric parts. You with me or not? So let's call this one A1. The area I want would be A times the area A1. Let's just zoom in there and what's going on in this first quadrant. Remember, when it comes to polar coordinates and area, you're always going from the pole out to the curve. So if I start off here and I start rotating counterclockwise, I'm going from the pole out to what curve? This curve is r equals 2. You with me or not? And then at some point, at this angle here, it switches, doesn't it? You follow? It switches to the blue curve, which is r equal 4 cosine 2 theta. You follow or not, folks? So what do I need to do? I've got to figure out the angle where these two graphs meet. So that's where we have to do a little bit of algebra. But do you see how it's made up of these two different pieces? The first piece, we're going from the origin out to the r equal 2. And then the second piece, we're going from the origin You see why there's two parts to this or not, folks? Okay, so you're always going from the origin out, sketch it out. So we need to know where these graphs intersect. And we saw on Friday that that can be a little dicey when it comes to polar coordinates. So we can start what we normally do and just see if we get the answer we need here. We'll just set the r's equal to each other. So I need to know where the cosine of 2 theta is a half. Well, just cover this up. Where is the cosine of something a half? Pi over 3, 5 pi over 3, etc. So what would theta be? Does that look good here or not, folks? Right? That's the winner. Here's our theta. So once again, thanks to symmetry, I just need to find the first place it happens. And then I'm going to have two integrals from my answer. So the area I want is going to be the sum of two areas. It's going to be the first area and then the second area. I'm going to keep it color-coded here. The first area is going to be the area from the pole out to r equals 2. So it's a circular sector. We could actually find this geometrically. That's going to be the 1/2. I call this area 1 here. It's going to be 1/2 the integral from theta equals 0 to theta equals pi over 6 r squared d theta plus 1/2 integral. And now we're going from pi over 6 to where it crosses through the pole. And in the previous exercise, we know that it crosses through the pole when theta is pi over 4. And then I take my final answer there and multiply it by 8. But do you see how we're working with the graphs to help us figure out what the integrals are? That's what I recommend. Graph it. You got Desmos, it's fast. You've got your trigonometry graph that you can use to double check these. Right, so we're doing it's r equals 2 from pi over 6 to pi over 4. There it is. We got r equal 2. I guess it doesn't give us a choice for that. But that part is the part that that just comes in right there. Okay. So once again, these thetas in number 3 should be 2 thetas. I'll fix that right away and upload a new version of it. And there's your homework.